we will first of all finish this part, and then next, the part 5 of this chapter would also be about a particular example for the motion relative to the Earth, which is known as the Foucault pendulum. Okay, so but for that part of the chapter, you will not be tested in the final exam. Okay. So that is to say, for our final exam, okay, so up to this part of the content will be tested. Okay. So then today, basically, after I want to finish the content that will appear in your final exam, then I will actually go back to my office and get back the midterm papers, and then return them to you. Okay, and then after that, I'll continue on the content that basically will not appear in the final exam. Okay. So then let's begin with this. So last time we were considering some motions, right? So of particles, right? So on the surface of the Earth, right? So in particular, basically, we just have a free falling particle, right? So the only real force that we were considering is the gravity, right? So and then the other forces are just the fictitious force, right? So in particular, we focus on the effect of the Coriolis force. Okay, so you may still remember this example that we did last time, is that I have a person standing on the top of the building, and then he or she drop a ball, right? So to the ground, right? So and you would think that so it would just follow an exact straight line, this red line, just and then get to the ground like this, right? So but it turns out that so because of the fact that we are on this Earth surface, and then the actual trajectory will not be a straight line, and then at the end, when the ball reaches the ground, okay, so it has a slight horizontal displacement. Okay, and last time I also introduced this method that I call the perturbative method, right? So basically, what we did here in the example is that we are not really looking for the exact solution for the trajectory, right? So it is just an approximate solution, right? So is that we start from the solution where we assume that there is no Coriolis effect, right? And then in that case, what you get is just this simple minus GT, right? So for your velocity function. And then from there, right? So we know that this is not the correct trajectory, right? So and then from there we calculate the Coriolis force, right? So omega cross V term based on this, right? So we calculate the Coriolis force essentially based on a solution which is not exactly correct, right? So but we know that this is already pretty close to the real trajectory, and then from this we calculate the force, Coriolis force, and then calculate the acceleration of that particle due to this Coriolis force, and then find the so-called the correction to the trajectory, right? So for the particles, right? So you can see that this is not the exact solution. And last time I also mentioned that in fact, in principle, we could find the exact solution if you want to consider both the real force and the exact the fictitious forces. Okay, so but for that one I'll just talk about later. Okay, so in the following examples I'll just still focusing on this method where the solution is just approximately true. Okay. So and before I move on to the next example, actually I want to just give you a bit intuition, right? So now I have this calculation, right? So I know that there's a deflection here. So, but if I want to just go back from the viewpoint of inertia frame, so how should I understand this deflections? Okay, I want to forget about a set of rotating frame and fictitious forces for a moment. Go back to the right, that's the inertia frame. How do I understand this deflection? So what you can think of is the following. Okay, so just let's say for simplicity, let's say I'm doing this experiment, this ball dropping experiment. Okay, so at the equator, let's say. So this is the building, right? So and then I drop the ball. So if you are, let's say you are an observer which is at rest, right? So let's say you're looking at the Earth, right? So kind of from the North Pole, like so, and then what you see would be the following, right? So yeah. So what you will see, right? So from top, right? So you will see kind of this is what you see, right? So you see the Earth, and then you see this part is the North Pole, and then you see that someone is trying to, right? So this is the building, right? So it's exaggerated, and then this is the ball that is dropping like this. So and this is the rotation of the Earth, right? So you see the whole Earth is rotating. Okay, so yourself is not in a rotating frame. Okay, so now let me just draw this part again. So let me just kind of draw this part out, right? So and then what you see is the following, right? So the Earth. So this is basically this part, right? So the ground, and then the ball is like dropping like this. Right? Okay, so initially, before the person released the ball, okay, so actually from the viewpoint of a fixed observer, this ball is not at rest, right? So why is that? Because the whole thing is rotating, right? So for example, if I just look at, so this is the radius of the Earth, right? So and then this point is the ground, and then actually the point of the ground has a velocity which is equal to r times omega, right? And then what about this? So then this distance is capital R plus small r. So therefore, before you release your hand, actually the ball already has a velocity which is equals to big R plus small r times omega, like this, right? So that is to say, right? So before you even like drop the ball, you're still holding it, but it already has this velocity. And then, as I said, so this is the point of the ball, which is directly below this ball, right? So and then actually, right? So this point is also moving to this side, right? So with this velocity, okay. Okay, so then from here, you can already see that what's going on. So this velocity is actually slightly bigger than this velocity over here. right? So there's a small R, right? So then as it drops, so that means that now it has the velocity, this component of the velocity, right? So therefore, it is faster than this one, but then now it starts getting closer and closer to this point, right? So therefore, you will expect that after some time, okay, so maybe the ball would be somewhere here. Right. It is slightly faster than this one. So relatively, so this one has to lead a little bit, right, with respect to this point. Okay. Okay, so however, if you just use this two comparison, you're still not going to get quite the correct result as we got from this calculation. Okay. So because now you also need to understand that when this ball drops, right? So let's say, right, so let's say this is the center of the Earth, right? So initially, right, so acceleration is directly to this, along this line. Right? So then now that once it reaches here, then if you again draw a line which is joining this point and to the center of the Earth, right? Now you will see that the acceleration direction would be more like a little bit like this, right? There's a little bit, there's a little component which is to this side. So then this little component, so in some sense, will also, right, so slow down this velocity a little bit. Okay. So if you don't consider this small component, right, so you will think that when this ball reaches the ground, right, so it will have some difference. Okay, so but that difference would be bigger than it actually is. Right, so because of this small component to the other side. Okay. But at the end of the day, so this ball will be a little bit ahead than this point. That's true. Okay. So this is just try to give you some intuition. Okay, so about does everything make sense? Right. So if we go back to the inertia frame, so how do I actually understand this deflection? Okay. Although this is not really extremely important. Okay, so when you deal with the problems, okay. Okay, so the second order diffraction I talked about last time. Okay. Now let's do a very similar example here. So instead of dropping the ball from the top of a building, so this time the person is standing just on the floor, and then he or she just throw the ball vertically up, right? So like this. So if there's no any Coriolis force effects, so what you expect is that the ball will just follow this dashed line, so go up and then go back down. But it turns out that due to Coriolis force, right? So when the ball reaches the ground again, so it's not going to go back to his or her hand. So instead, it will go back to go to this point here. So this is interesting, right? So because in the previous example, when we have the person on top of a building, And if this experiment was done, so the deflection is to this side. Okay. So this time, if you do this experiment where you stand from the ground and go vertical up, and then the deflection, as you calculate, will be to the other side. Okay. So we'll see the calculation. Okay. So, but this is a difference that you might want to take note on. Okay. So how do we do this problem? Okay. So compare to this. So again, we use the same strategy. So first of all, we just work out the motion, pretending that there is no any fictitious force effect, right? So just like the first step here, the first step here. Okay. So compared to this experiment, so the V naught T that we have this time is actually rather similar, but we just have a non-zero initial velocity, right? So we have a non-zero initial velocity, which is let's say is u, right? So the initial velocity is in the positive z direction. So I just write u z hat. So therefore, the velocity of this particle, if we ignore any Coriolis effect, then it will be like this, right? So u minus gt. So instead of just minus gt in the last example, okay. And then I assumed that this ball can reach the height h, right? So this capital H is the same, basically is the same h as this building, okay? So, and of course, from conservation of energy, so that means that you know the requirement for the u. So u is given by square root 2g h. And now, okay, so then that's it, right? So we are ready to calculate the Coriolis term, right? So again we know that this will be along the y direction, the Coriolis, the acceleration due to Coriolis effect, right? So it's just minus 2 times omega cross v naught. So and then let me just write down the final answer, right? Just so what you have is the following. So basically, it's just this one, right? So but now it's not, this is not minus gt, right? So this is u minus gt. So like this. Okay, so then if you just integrate this equation twice, right? So you get the y would be equal to omega cosine lambda t squared times dt divided by 3 minus u. Okay. Okay, so then we want to find the delta y, right? So that is when the ball reaches the ground again. So that would be y when t equals let's say capital T, right? So it takes that amount of time for the ball to go back to the ground. So what is capital T? So capital T here, it just basically would be 2 times this. Will be 2 times this square root 2h divided by g. Right. So that is y 2 times square root 2h divided by g. And again, you can just work out the math by yourself, but at the end, this is the answer. So here you can see that you have a minus sign in front, right? So compare to this one, you have a positive sign. So then it explains why you have the deflection to the other side. Okay. And another interesting question you can ask is that so that means that okay, so you expect kind of like the trajectory, okay, is something like this, right? And what about when the ball just reaches the maximum height? So what about that deflection? What about this distance? That is, right? So you can also work that out, right? So just put y when t is equal to 1/2 of the capital T. And that you actually get exactly half if you substitute the number. Okay. So next, the situation is a bit different. Okay, so in the previous examples, we are just considering either the person is trying to let the ball go down or let the ball go up. So this time the experiment is as follows. So this person is trying to throw the ball. Okay, so just horizontally forward, okay, like this. So that is if I'm going to draw the person, so it's like this, okay. So it's throw the ball to this side horizontally. So to the east, okay. So in this picture. So if you don't consider any Coriolis effect, then the trajectory will just be like this, right? And everything just stay in this YZ plane, right? So that is the ball is not trying to go out of the screen or go into the screen. So if you don't consider any Coriolis effect. However, as we will show, once you consider the Coriolis effect, then well, the ball will kind of still doing something like this, but actually the trajectory will go a little bit out of the screen. Okay, so if you look from the top like this, okay, no Coriolis effect, then so you're looking at from the top, you're looking, this is the head of the person, right? So you just go along this line. So with Coriolis effect, so the trajectory is bent like this. Okay. Then we want to calculate this time this deflection. Right, so last time we calculated, we focused on the deflection, right? So along the y direction. So that is either east or west. Right, so this time want to consider the deflection along the x direction. That is either north or south. Right? But the procedure really is the same, right? So, but it's just that how you give the initial the zero order solution, right? So that is again, we start with the case where you pretend that there's no Coriolis force, then the trajectory, how does that look? So this time it looks like this. Right. So in the previous examples, you only have everything in the z direction. So now you have this new term in the y direction. Okay. And then you expect that because of this component, then once you do the cross product, right? So with the omega term, then you will get the components in a new direction. Okay, so so then the procedure is exactly the same as I said, right? So now if you actually do the cross product, right? So you should actually get the accelerations that will have all three components. Okay. So, but as I said, so we just want to focus on the deflection. So along this x direction. So then the x component. So the x component of this term is given by this. And then if you go ahead and again, well, integrate twice and then substitute the t equals to capital T, then you are able to find the deflection. Okay, so along the x direction. Okay, so then that's the examples that I want to go through. That you could imagine that you can do something even more complicated, right? So, for example, if the initial velocity is not horizontal, right? So you can just throw the ball a little bit up, right? So like a real projectile, like a projectile motion that we usually see, and then you can still do all the calculations by using the same procedures, right? So, or you can try to have the person like throw the ball to the north or south, right? So instead of to the east or west. Okay, so okay, I think we have to pause here. Okay, so I have just returned your midterm, and so this chart shows the distribution, and so this is the mean, and this is the standard deviation. So I will upload the solution, then marking scheme to the Blackboard soon. Okay, so you may want to check the marking. Okay, so and if you find any problems, okay, so with the marking, okay, so do the following. Okay, so listen carefully. Okay, so so there are 6 questions in the midterm, right? So and then we have 3 TAs. So each TA graded 2 of the questions for all of you. Okay. So therefore, if you have problems, okay, so with the marking on a particular question, so you have to go to the TA who is responsible. So 3 TA. So let me try. So Meng Chenqi, so he graded question 3 and 4. Okay. And Deng Yatou, he graded question 1 and 6. And Zhang Yuhong graded 2 and 5. Okay. So if you have problems, go to them, right? So you find their contact information in the course outline. Okay. So if the problem is not resolved after communicating with them, then you can come to me directly. Okay. So if there's some obvious mistake, like when they sum your mark, okay, so some mistake was made for that obvious mistake, right? So you can just come to me directly. Okay. So, but if there's your problem is related to the details on the judgment, okay, so then just go to them. right? So the reason why I divided the gradings in this way, right? So just try to be fair, right? So then they apply the same judgment, right? So to all of you. Okay, so then let's continue. So to finish our chapter. So I mentioned this last time, right? So I told you that although we were focusing on doing the perturbative solutions, so but actually, right? So exact solutions can be found. Okay, can be found. So but however, when I say exact solutions, okay, so when in the equation of motion, okay, I was dropping some of the terms. Okay, so the exact means that after I drop some terms, okay, so that solution is exact. Okay. So that is in ultimately, right? So this is, I'm still not talking about the exact solution of the real problem. But anyway, let's see how it works. Okay. So we have been just neglecting the centrifugal force, right? So we have been just focusing on the Coriolis force. Then this is what I have, right? So if I want to do it exactly, so that means that I'm going to really solve this equation, right? So without any approximation. Right? So can we do that? So you can just kind of look at the structure of this equation, right? So then this v vector is, in principle, is just x dot x hat plus y dot y hat plus z dot z hat. And therefore, this equation of motion, right, so can be decomposed into three equations, right? So what you have would be mx double dot equals to something, right? So my double dot equals something, mz double dot equals to something. And what do we have on the right hand side? Right, so your right hand side, right? So because of this omega cross v term, right? So you can either have, right? So x dot, y dot, or z dot, right? So some of them. So therefore, if you want to solve this equation of motion exactly, so that means that you are going to solve this system of differential equations exactly. And this system of equation of motion, of course, form a set of coupled differential equations, right? So because this x double dot on the right hand side, but then on the left hand side, but on the right hand side, you might have y dot or z dot. But even that's the case, right? So you expect that you should be able to solve that without much difficulty, right? So because for coupled equations, right? So you have learned how to solve that in last semester in 2051. And how did you solve that in that course, right? So there are actually two methods that I taught, right? So one is to use elimination of variables, right? So the other is that you can just write the system of equations as a matrix form, and then right, so find the eigenvalues and eigenvectors. But here, right, so let's actually go into the details of solving this equation of motion exactly, right? So if you just go ahead and write out all the three components, right? So you I give you the G and the omega, right? So, and then if you actually go to break it down into three equations, so this is what you have. Okay, no approximation is made, right? So x double dot depends on the term with y dot, right? So y double dot depends on two terms. The first term is with x z dot, second term with x dot, right? So finally, the z double dot depends on this y dot term and also a constant term. So here, right, so I just use the method of eliminating variables to solve this set of equations. So what I do here, so for these three equations, if I integrate them once, then I have this set, okay. And then after that, if you substitute this equation 4 and equation 6 back to equation 2, then you get this. Right. So what is the goal here? So the goal here is to basically get rid of, so for a particular equations, I want to get rid of the other variables. I just want to have all the terms to be depends on one of the variable only. Right. So in this case, I'm just going to set up this equation such that only the y variable is involved. Right. So like this. And this is just a second order, right? So linear ODE, right? So although it is a inhomogeneous ODE, but you know how to solve easily, right? So complementary solution and particular solution. Right. So if you do that, and also with the and then this is what you have. And here, right? So you also need the initial conditions, right? So the initial conditions I give you here is just, I think it's just assuming the free falling case, right? So start from red. And now, right? So you have the y as a function of t, right? So you can just put this back to equation of 4 to get x dot, then you get x, right? So and then also get substitute this to the equation 6, then you get z dot, which is you get z. Okay, so then you see that you actually have the exact solution. Okay. However, as I mentioned in the beginning, I dropped the term, the centrifugal force. Okay. So if you want to include that, then the equation of motion that you solve would be this full equation. Okay. And I'm not going to actually talk about how to solve these full equations because it's more complicated. So for those who are interested, might refer to this article here. I'll come back to this slide a bit more at the end. But let me also consider another special case. So this time I drop the Coriolis term and just intentionally keep the centrifugal term. So what about this? Can I solve this exactly without much difficulty? Okay, and the answer is yes. Okay. So however, this one, well, you may say that this one is not so meaningful, right? So because the Coriolis term is more important than this term. So in our scenario, okay. So therefore, when I say that I drop this term and keep this term, it's kind of still well justified because this term will give you more significant correction compared to this. But now you are saying that I'm dropping the more important term and keep this term and want to play with it, and of course you can do that. And but that might not be so meaningful in some sense. But anyway, so I just want to show you that if you do that, you can still solve it exactly, right? So and it's not surprising because again you are just going to solve a set of coupled ODEs, okay. And therefore, I'm not going to go into details for this one. Okay. So now, if I want to just go back to think about the corrections. Okay, so now you may say, okay, so I have the exact solution already. So why did we bother to work on the perturbative solutions? Okay, so in the first place, right? So because I told you that even I have the full equation, it can be exactly solved. So that's well the first reason. Okay, so the practical reason. So at least, okay, so this is not very convenient, not very easy. Okay, so if you look into this paper, okay, so that's I would say that's one reason. Okay, so the other reason is that even I exactly solve this full equation of motion, you are not really getting the exact solution to the real problem. So why is that? Because when I write down this equation of motions, I have already made an approximation in this term, this mg. Right. So when I say this mg, so that means that I'm assuming that, right, so the acceleration due to gravity is just a constant number. But you know that in principle that's not exactly correct, right? So because of the 1/r square gravitation law that we have learned, right? So therefore, right, so to be exact, you will need to replace this term, right? So with the 1/r square law. So if you actually replace this with 1/r square law, right? So then I believe that you cannot get the solution easily. So and here it's just a table. Okay. So today and also from the last lecture, so I told you that, right? So from the perturbative solution, so I get the so-called correction, and I told you that if you want to get a better and better corrections, right? So what you can do is that first you put in a zero order solution, and then you get the corrected result. And then if you want to even do better, then you just substitute the corrected solution, right? So to the correlative term, and then do the calculation one more time. And this is just a summary, right? So if you consider free falling particle, if you just consider the so-called the first order correction, so this is what we have. Okay. So I think I gave you the real number, right? So you said if you drop it from like 100 meters, and this one, the correction is about 1.5 centimeter. The second order correction, which is much smaller. You know why it's much smaller, right? So because for the second order correction, it depends on omega square instead of omega. And in our case, right, so omega is a very small number, right? So omega, you know what omega is, where you know it takes 24 hours for the Earth to complete one revolution. And if you just calculate the number of omega in terms of radian per second, then you know that this is a very, very small number. Okay. So but anyway, so that's why omega square, if you have a correction term which depends on omega square, then it will be even much smaller. And if you keep going, right, so even you get a omega to the higher power term, then the correction is just getting tinier and tinier. So this is what happens with the Coriolis, right? So what about the centrifugal, right? So the centrifugal term, because you know that it comes from the omega cross R, right? So that means the omega, there won't be an omega term, right? Because you always have the omega cross omega, right? So then the at least the first correction term, the lowest order correction term, will appear as an omega square term. Okay, they won't appear as a linear omega term. And because of that, well, you expect that the centrifugal correction would be much smaller than the Coriolis correction. Okay. And in fact, right, so this is how the first correction term due to the centrifugal force looks like. Okay. So that if you look at this and this, you kind of expect that, right? So they are comparable. So therefore, once you want to get better and better corrections, when you solve the equation of motion, you cannot just keep the Coriolis term anymore, right? So because once you get the second order Coriolis corrections, then that would already be comparison to the centrifugal correction. And if you get the higher order, one more high order of the Coriolis correction, okay, so without considering the centrifugal correction, you know that then that won't be meaningful anymore, right? So because you're missing a significant part of the correction, so relatively. Okay, so then that's the end of this part of the chapter. So the next part of the chapter, which is also the last part of the chapter, won't appear in your final exam. Okay. So this is still talking about the motion of a particle, so on the Earth's surface. Okay. And historically, what we're considering is a very famous experiment. Okay, so this is known as the Foucault pendulum. So this is an experiment done in the 19th century. Okay. So and this experiment gives the simple direct evidence to tell us that the Earth is rotating. So basically, this one is without relying on astronomy, right? So and just everything is just done in a room. Okay. So the setup is the following. Okay, so this is the so-called Foucault pendulum is just essentially is a pendulum that you have learned, right? So you can just imagine that you have a simple pendulum where you have a string and a mass. Okay. So this is a picture. Okay, so this is a picture. So and to show you how it works, so let me just draw this table. Okay, let me draw this table from top. Draw the top view of this table. If you look at this table from top, it looks like a circle like this, right? So if you have this Foucault pendulum being swinging, then what you expect is the following, right? So if you just start, let's say if you pull this mass, right, so to this side, right, so then what it does is just this, right? So swinging motion like this. Okay. Then if you just look from above, right, so then basically you see that the trajectory of your pendulum is just doing something like this, right? Just a line. But what actually happens is that if you wait for a few hours, okay, if you wait for a few hours and come back to look at the pendulum again, so what you see is that now the plane of the motion of the pendulum has changed. So it's become something maybe like this. Okay. And then after some more time, so you imagine what happened, right? So the plane of the oscillation keep rotating. Okay. And eventually, right, so it go back to the original plane. But just keep doing this, right? So with a constant velocity. So the plane of rotation, the plane of oscillation is keep rotating at a constant rate. Okay, so that's what this experiment shows. Okay, so now let's understand how it works, right? So let me consider a special case first. Okay, so just forget about this, all these equations here, but just let's look at this special case of the experiment. Okay, so where you set up your pendulum at the North Pole. Okay, and then just let it swing. Right. So then you know that it takes 24 hours for the Earth, right? So to complete one revolution. Then if you just have this plane of swinging to be constant, to be fixed, then according to an observer who is actually rotating, we'll see that this plane, right, so actually rotates. So in this special case, I think it's quite easy to imagine. Exactly 24 hours, right? So the plane of rotation complete, right? So because this Earth is rotating, but this plane is, according to a fixed observer, is not rotating. So therefore, the observer on the Earth will think that the plane of oscillation is rotating. So with a period of 24 hours. Okay, so of course, we do have one technical details here, right? So you would imagine that, okay, if you say, okay, so now I actually, how do I set up this pendulum, right? So this pendulum is in a building, right? So that means that there's a ceiling of the building, right? So this is a building. And this is the point where you fix the string for the pendulum, right? So then the building itself is actually rotating with the Earth, right? So and that means the ceiling of the building is rotating, right? So therefore, when you design the pendulum, you cannot really keep this connection to be a fixed connection, right? So because you could imagine that if it is really a fixed connection, and so this is a fixed point, that as the ceiling rotates, so that means that you will provide the torque to the string, right? So and that might by itself, right? So make the wire be twisted, right? So I'm exaggerating. Then that might actually make the ball spin. So I don't want that. Okay, so I want to have a setup in a way such that, right? So as the ceiling is rotating, as the building is rotating with the Earth, right? So there will still be no torque. Okay, so in the string. So that's one small technical detail. Okay, so but that can be done, right? So if you have some kind of bearing, okay, so to make this point, then you should be able to do that. Okay, so then if I look at this case, it seems to be quite easy, right? So 24 hours, I can explain that rotation of the plane. However, well, the experiment was not done in the North Pole, of course. It's done at some latitude. And what you will find if you've done experiments here at some latitude is that the period of the rotation of the plane is actually not 24 hours. It's a time that is longer than 24 hours. Okay. So that's a kind of a much less intuitive. Okay, so but here we'll try to solve. Okay, so for the rotation period. Okay, so of this Foucault pendulum. Okay. So in the actual setup, I don't remember the exact number, but the length. Okay, so the length of this string is I think is maybe 50 or 60 meter high, and then this mass. Okay, so maybe in the order of 10 kilograms of mass. Okay. So the reason why you want to make it that long, right? So it's because what we want is that the small angle approximation, right? So because we want this pendulum to behave like a simple harmonic oscillator, then you understand that you need the small angle approximation, and if you want small angle but you want the amplitude to be not so small, right? So then what you need would be a long string. So, and on the other hand, right, so you want a very large mass, right? So because you want it to be very stable. Okay, so then as I said, so this is a pendulum problem. So then let's look at the how to formulate this pendulum problem. Okay, so well, in the pendulum problem, when we talk about the pendulum problem where the plane of oscillation is fixed, right? So usually we just use theta as the coordinate. So here, because now you know that we are not fixed, not having the oscillation plane to be fixed, right? So you understand that we are really talking about a two-dimension problem here. So therefore, I'm no longer using theta as the variable, and it turns out that using x and y would be the convenient choice for this problem. Okay, so as used. So this is the setup here, right? So you could imagine that if you just extend the string really up high, right? So then you have you kind of have a theta here, right? And then let me define this to be phi. Okay. So this mass is free to move anywhere, right? Okay, so equation of motions. And approximation here is that because I'm still making the kind of the small angle approximation actually, but because of the fact that this L is very long, then this displacement might not be that small. Okay. But what you could expect is that, right? So if the theta is small, right? So then basically the change of height of this mass as it swings will be very small. Okay. So therefore, I'm really approximating it as a two-dimensional problem, right? So although, right, so when this mass is out here or here, there's a small height difference, but I neglect that. So therefore, I'm just considering the XY plane. Okay, so now I consider the x component of the force and the y component of the force, right? So then that is of course provided by the tension, right? So the tension of the string. Okay. Then this tension, this Tx is given by this, and this Ty given by this. So why is that? I can let me try to actually break down the component and use T. Okay. So the Tx would be, first of all, I want to get the horizontal component of this T. Right. So that, what is that? So T sine theta. So T sine theta would be the horizontal component of this T. And then if I want to just take the x component, then that would be sine theta and then multiply by sine phi. Okay. So what is sine theta and sine phi? Sine phi. Okay. So if I just assume that this vertical length is h, right? So and then if I assume that this horizontal distance is r, small r. So and this length over here is L, right? So then if you just use this triangle, right? So then you just find that it's just equals to T times R divided by L times Y divided by R. Right. So and that would just be T times Y divided by L. Okay. And I have this minus sign here because it's towards the negative direction. Okay. So similarly, if you want to find the y component, then that would be T again sine theta, this time times cosine theta, cosine phi. So then that would be T times R divided by L times x divided by R. And that would be T times x divided by L. Okay. So then that's the same thing over here. So now the approximation that I want to make, as I mentioned in the beginning, is that there's no motion in the z direction. Okay. So then if that's the case, right? So basically, I'll be just saying that the T is just to balance the mg. Okay. So therefore, the approximation is that T is just approximately given by mg. Right. So therefore, right. So the mx double dot given by approximately given by minus mg times x divided by L. Right. So similarly, my double dot is given by minus mg times y divided by L. So then you cancel the m, then you get these two equations. Okay. Okay, so then this is just considering the real force. So now, of course, we want to consider the Coriolis force. Then again, we are going to look at the omega cross V term. So the omega cross V term given here. Okay. So here you can see that the strategy that we use this time is a bit different from what we had last time. Right? So last time, what we did is that we just look at this equation of motion, right? We solve it, and then we plug it into the omega cross V term. Right? So, but this time we are doing something better, right? So we are we are in the sense we are trying to find the exact solution. So although the approximation have been made here already, so we are trying to make the exact solution in the sense that here we don't really substitute the solution of these two here. Okay. So we actually treat them as the V itself. Okay, so then if I just do this omega cross V term, then the X component and the Y component are given over here. Then the equation of motion, right? So it's given by these two, right? So this X component go to the first equation, this Y component go to the second equation. Okay, so again, I'm negating the centrifugal term. Okay. And because you know that the centrifugal term, right? So will basically not affect the motion along the XY plane. Centrifugal term will just tends to, right? So just push you away from the Earth's surface. That should just go along the Z direction. So that's not relevant in this problem. Okay, so but anyway, so this is the equation of motion that we are going to solve, right? So again, couple equations of motion. Do we know how to solve this? So in the chapter of couple oscillator, right? So what you have was something similar, but not the same, right? So what you had in the couple oscillator chapter, well, you usually have the second order derivative on the left hand side, right? So but then on the right hand side you don't have any derivative. Right? So this time I have the derivative terms also on the right hand side. So then how do we do that? Okay. So in fact, just try to again write it in the matrix form. So in the textbook, so if you just follow the textbook, it didn't really say anything about making it into matrix form and diagonalization. It basically just gives you this trick. Okay, so and then it's just telling you that you just add this first equation with the second equation with an extra factor of I, then you get to this. But if you just jump into this step, you might not feel very comfortable. Right? So where does it come from? Right? So then what I want to show you is that if we just want to go back to something we have learned before, right? So just look at this couple set of equations and then see the matrix form first, right? So if you convert it into matrix form, it looks something like this. Okay, so this is something that is not so unfamiliar to you, right? So except that now, as I said, I also have a derivative term on the right hand side. However, even that's the case, so what you could imagine that if you can diagonalize this matrix, right, then still you should be able to solve this problem, right? So because if you can diagonalize this matrix, then you will be able to decouple these two equations. Okay. So then this time, I'm going to diagonalize this matrix. So this is not a diagonal matrix, right? So diagonal matrix is that these two has to be non-zero, and then these two has to be zero. Okay, so don't be confused. This is not a diagonal matrix to start with. So if you actually try to diagonalize this matrix, you realize that complex numbers appear. So remember, in the last semester, I told you that if you have a symmetric matrix, then the eigenvalues are guaranteed to be real numbers. However, if you have an anti-symmetric matrix, then it's guaranteed that the eigenvalues are imaginary number. Right, so then that's exactly what you get here. If you diagonalize this, then this is the diagonal matrix you get with the two eigenvalues being purely imaginary. Okay. And then again, right, so the matrix on the left and on the right, remember how you construct them, right? So you just construct them by putting the two eigen vectors together. Right, so and because you have this imaginary eigen values, then it's not surprising that the eigenvectors also contains complex number. Right? So, but anyway, I am able to diagonalize this matrix. Then follow the exact same procedure that you have learned before. Then you realize that now this set of equation of motion can be rewritten as this. Right, so where this new variable PQ is given by, there's a typo here, given by this matrix times XY vector. Okay, so and in expressing the same set of equation in terms of P and Q, then you find that they are decoupled, right? So P, the equation for P does not contain Q, right? So then the equation for Q does not contain P. Okay, so now you know how to solve these two equations, right? So just a second order ODE. Again, you can use the characteristic equation, the auxiliary equation. So although, right, so there is a complex coefficient here, but that's okay. The same method can be applied. So then you solve for P as a function of time, PQ as a function of time, then you can get back X and Y. So in fact, I only need one of them. Right, so if I just consider this, okay, so you are able to get the solution Q of T equals to something. And now you look at what you have over here, and what it tells you is that Q is actually equals to X plus IY, right? So once you solve for Q as a function of time, and then you just write it as this form, right? So some real part plus some imaginary part, then you know that this part would be your X and this part would be your Y. So then that's how you deal with the problem. So therefore, you go back to, so just remember this, like Q equals X plus IY. So then if you go back to what I have here, right? So this is exactly what I'm doing. So multiplying the second equation by I, and then add it to the first equation. Then you can see that I have this X plus IY term, and that's exactly Q. So then the equation of motion becomes this. Okay. And then the solution is written like this. Okay, use the auxiliary equations. You should be able to find the roots, and then that's the solution. So now one approximation to be made is that the alpha should be much greater than the omega z. So why is that? What is alpha? So alpha is the square root of G divided by L. Right. So that's exactly the angular frequency of that swinging motion. So how long does it take? Right, so for the pendulum to complete one cycle, right? So in the order of seconds. And now, right, so the omega z is omega times sine lambda. Right. So omega is the Earth rotation, as I mentioned earlier today already, right? So this is a very small number, and then times some point something, and it's omega z is a very small number. Right? So therefore, alpha much greater than omega z. So therefore, in this term, so I just simply write it as alpha and minus alpha. Okay, so this is nice, right? So using complex number to solve problems. But at the end, we are going to convert this back to the sine cosine function. Okay, so now if the Earth is not rotating, so I set omega z equals 0, then in this case, I will just denote the solution as Q naught, which is given by x naught plus I y naught. And in that case, right, so basically just set this number to 0. So that is this x naught t plus I y naught t is given by this. And then therefore, right, so the solution Q can be written as a product of the Q naught and the extra factor here. Okay. So then this is what I write down. Okay. So now time to equate the real part and the imaginary part. Right? So the real part for the x, imaginary part for the y. Okay. So like this. So now the sine cosine function coming out, so that makes you feel comfortable, right? So that's what you expect. Okay, so you understand that. First of all, you know how the x naught t and the y naught t would behave, right? So those would be sine or cosine function with alpha as the angular frequency. So now I have this results here, and then you see that there are some sine cosine term which contain the omega z, right? So the Earth rotation frequency. Okay. So to make it more transparent, let's write this solution in the matrix form. Okay. So like this, in the matrix form. So then, when you look at this matrix, it reminds you of a rotation matrix. Right? So this is exactly a rotation matrix. So if you have a pendulum, okay, so without Earth rotation, again, if I just look at the behavior, right, so along the xy plane, right, so you would say that, okay, so the plane of rotation always will be along a particular line like this, depending on your initial condition. And then, right, so any point on this particular line is given by x naught t, y naught t. Right, no Earth rotation. That's what you have. X naught t, y naught t over here. So now, with this rotation matrix, right? So what happened is that, right? So this plane will be rotating, and that's exactly what we expect, right? Oscillation while the plane is rotating. So then, what about the rotation frequency? So previously, I told you that if it is exactly at the North Pole, right? So it will exactly take 24 hours. However, if you're not, then that will not be 24 hours. So the rotation frequency is given by this omega z. And remember, this omega z is related to the Earth rotation by this equation. It's omega times sine lambda. when you're exactly at the North Pole, right? So lambda is 90 degrees. So that omega z is just omega. But if you're not, then this sine lambda is smaller than 1. Then you have the rotation frequency actually smaller than the Earth rotation frequency. So therefore, if you are somewhere here, maybe it will take more than 24 hours. Well, it will take more than 24 hours. Maybe it will take more than 30 hours. Right? So maybe 1 day and a half. Right? So to see a complete rotation. And also, if you do the experiment at the equator, that's interesting. Actually, you won't see any rotation of the oscillation plane at all. Right? So in that case, the sine lambda would be 0. Right? So finally, let me show you a little animation thing from the Wikipedia. So I think there's so this one. So look at this animation here. So what we are looking at, this little triangle here is the plane of oscillation for the Foucault pendulum, right? So at this moment, right? So when it's up here, so you can see that arrow is pointing up. So after 24 hours, come back here, the arrow is pointing down. So what does that mean? So that means the plane of rotation has rotated by 180 degrees. And then after another day, this arrow points up again. So then you can see that, right? So at this particular latitude, right? So it takes 2 days, right? So for the plane of rotation to complete one full revolution. And as I said, if you move it up or move it down, then the rotation period will change. Okay, so that's the end of this chapter 6. Okay. And as I said, the part of Foucault pendulum won't appear in your final exam. And next time, the last week, we'll have chapter 7, which is also about rotation. Okay, but the rotation of an extensive object. Okay, so not just particle anymore. Okay, so I believe that you have learned the basics like the moment of inertia and angular momentum. Okay, so in chapter 7, we'll go deeper into that topic. Okay, but so again, the chapter 7, the next chapter, won't be in the final exams. Okay. And one more thing is that, but for the exercise class next week, okay, so the topic will still be about chapter 6. Okay, so then you might still want to go to that one. Okay, for your revision for the exams. Okay. Okay, so then that's it for today. One thing I want to mention also is that if you you may help me to tell your friends, but if they didn't come today and if they want to get back the exam paper, okay, so tell your friend that go to the TA. Okay, so go to Mr. Tang. Okay, so go to his office to get back the paper. Okay.